So we are on the second part of the data presentation, and we were on this slide basically saying that you cannot draw a line chart when the intermediate points are not valid, right? For this you need what kind of chart? Bar chart, because then the intermediate points don't make sense, okay? And then the non-zero origins is always an issue, and if you avoid, so basically here is the thing is that somebody may use a different origin just to emphasize a minor difference. So this starts at 2600 and goes to 2610. The difference is less than 1 or 2%, but it just looks too much. On the other hand, somebody may use a scale to show that it is even smaller than what it is. Actually, this is actually not to the scale, but if it would have been even smaller than that. And at 2600, this is what it is, right? So the question is, which one of these is right or wrong? Again, you have to justify your choice. And as I said, there is no single thing I can say, well, then this is always the case, but you have to justify your choice if you take anything non-zero, because zero is generally the right origin, but if you take anything non-zero, you have to justify why you are doing that. And then the question is, what is the height of what is the highest value that you should take? And so there is a rule in the literature, 3/4 high rule, that the height upon the width should be greater than 3/4. You cannot just have the graph all in the bottom here. And so this is the height of the graph, and this is the width. This is 1 to 1 right now. So it should not be less than 3/4. Make sense? What that rule is? That this graph does not satisfy that rule, because the height is very small, right? And so basically this would be the right thing to do if you didn't want to be biased in any way. A difference of 1 or 2%, if it is very critical, if it is $1 million difference, then obviously you would go there. The thing is, one thing that we will teach you later on is that 1% is not small and 1% is not big. It depends upon what that 1% has impact on, okay? And so similarly, the probabilities, when we go to probabilities, 1% probability may be very significant and one may be not be very significant. Depends upon what you are taking the decision for. You are taking $1 billion decision, then obviously 1% of $1 billion is a lot of money. On the other hand, if you are taking a $10 decision, then 1% is nothing, even 10% is nothing, even 50% is nothing. So depending upon that, this may be significant difference, right? I may not be. Yeah, go ahead.
I'm sorry, I don't understand the height there. I mean, do you mean the height between the line and the x?
Okay, so this graph actually has the width of so many inches right here. That is the width. If you take the highest point here, the x value would be the width.
But I don't know what is the x value.
Yeah, right. So the thing is, I'm not using the units here because we are talking about the width in inches. So regardless of what the unit is, this is the inches in whatever that is. Because this could be from 0 through 1 here or 0 through 100. That's not what that number will not use. It's just the width. Any other question? All right. Then, so this is actually, I just changed the topic here. Which basically, previously it was about how to draw it right. This particular slide and the next slides are about pictorial games. Means these are the things that people do to show that their system is better. Okay? And so you have to be careful when you read a paper with this kind of thing, or when you see a paper which is generally written after you. This thing is, after you have done something, somebody will write a paper saying that we are better than them, right? And then you read it. Or if you're reviewing a paper, then you have to know that this is fair comparison or not. So this is a pictorial game. Another one is to give a double whammy. Double whammy means that one graph would be enough to show that one system is, so for example, in this case, one graph would be enough to say that the throughput goes down very fast. Okay? But instead of that, you could say, well, the response time goes up very fast too. But that is given, because if the throughput goes down very fast, the response time will go up as well. So they are related metrics. So people will show it that it is twice as, it looks like it is twice as bad as it is. It is bad, but it is, same thing for the good part. Is if something is good, you could show two graphs which are related and say, well, look, it is good on this metric as well. And that is just a double whammy, which is just redundant information. And then plotting random quantities without showing confidence intervals. So here is a graph which says that this is my performance, this is your performance, mine is much better than yours. Looks like it, right? But if you really had to plot the confidence interval, which we will talk about later on, and we will learn a technique here that the confidence intervals allow you to compare two, and only if they don't overlap. If they overlap, then they are identical. So up to here, these two systems are same. Over here, there is slight difference after this crossover point. Right? So really, these systems are not very different. They are different, but not very different. Whereas they look very different here because they did not indicate the confidence interval. And then the pictograms are scaled by height. So here we are saying this has a performance of 1 and this has a performance of 2. But if you really don't read the number carefully, it looks like this has a performance of 4 because the area is 4 times. We have increased the height by 2 and the width by 2. So that the whole area, which is what the visual you get, looks like 4 times a square of what you should have there. Is it clear? Okay. And then cell sizes. Whenever you see a histogram, look at what they are doing here in the x-axis. I mean, actually, this is particularly when people talk about distributions, and they want to justify that these two graphs, histograms, came from the same data. Okay. If you want to justify that this is normal, you will use this. If you want to say this is exponential, you will use that. Right? Which one is right? Any ideas? Is this data exponential or normal? Okay, all right. We don't know really. The answer is we don't know. See, the thing is, the right way to find the distribution is by some other technique that we'll talk about in the next chapter. Okay, so this one can be misleading. Either one can be misleading. Okay, and so we will talk about as to how to find the distribution. But the point is that here what we have done is we have taken too few buckets. So we have one bucket which goes from 0 to 6, second one goes from 6 to 12. Here we have taken too many buckets, and so the graph looks very different. Okay, and so we have a method which really doesn't depend upon any of this. And then non-zero origin. Another way to present non-zero origin is to break the graph in the middle. So this one says that these systems are all very similar. First thing is that they have not shown the confidence interval, which is one thing, but otherwise, even if you don't show, they are between 10 and 12, 20% different. But to show that our system is really out of the ordinary is that we broke the graph here and 9 is right there instead of 1 or 2. Right, so we plot everything between 9 and 12, and so this difference of 2 looks very, very significant. Yeah.
If I want to draw this graph differently to be more clear, can I just do relative graph? I mean, just say this is relative to A and just...
Ratio.
Yeah, exactly.
Okay, ratio is coming up next.
Okay.
So, I mean, yes, you can see anytime, either one now could be, whether this is a right or that right is, I'm not saying that this is always right, but basically this is what the person who wants to show will use this one, right? And it is quite possible that this is what you should be doing, because this difference of 2 is going to make a big difference. So chart alone, mathematics alone cannot tell you what is right. It's the system which can tell you. You get that point? Is that depending upon the system, maybe the difference of 3 or 2 is very significant and you want to do this, and maybe you want to do the ratios and things like that, right? So that we will discuss in one by one after another. But here I'm just saying that this is a trick that people play to show that their system is much better than the others, right? And if you have to use it, but justify it, and then basically you have to particularly justify from the system's point of view, not from the mathematics point of view. All right, that brings us to our favorite cartoon, performance analysis rat holes. And so what is a rat hole? Anybody knows what is a rat hole? Have you heard the word rat hole? You must have heard. You never heard of rat hole?
Not in relation to performance.
Eh?
Not in relation to performance.
Okay, in other places. What is a rat hole? Okay, this is a common American lingo actually, I'm sorry, but basically the thing is, a rat hole is something that you go to a meeting and they will say, well, let's discuss this thing and that thing, and then people say, no, that's the rat hole. Rat hole means that is something once you get in, you cannot get out. That's an unending discussion. Unending discussion. And so why do you need to know what the rat holes are? Because if somebody is making a presentation, your competition, you just get them into a rat hole, right? And they will never be able to get out of it. And if you are making a presentation and they get you into this, then all you have to say is, I know that's a rat hole, so let's not get in there. Not now. So you don't even get into the rat hole. So basically the topmost rat hole is workload. You can question the workload of any study at any time on any paper, any presentation. Workload is never right. Why? Because either it is not current. I mean, if they did the measurement 2 years ago or just last year, well, this year has made a lot of difference. The workload has changed. You make a case. Or if they did a study of 5 systems, 5 systems make no difference. If there are 1,500 other systems or 15,000 other systems, obviously they cannot measure 15,000 systems. If they measured X, you say, well, X is not important, Y is more important. So workload is, regardless of what they do, you can always question it. Now, if you are presenting it and they bring it up, this is X and you are doing Y, well, so hold on. I know I'm doing X, but this is the best, we can do. On the basis of X, this is the conclusion I'm making. Yes, we can do Y too, but, we didn't do that or whatever reason. So basically, don't get into the rat hole, because you cannot justify your workload more than what we are saying, right? So workload is the most weakest point of any study. Second is metrics. So, all right, so you are using throughput, but who cares for throughput? We really think that the people really care for their time, and therefore response time is the most important thing. All right, if they did response time, then you say, no, throughput is more important. We are putting money in, and so we need to know how much money we are coming in, and the money comes for each transaction, not for the throughput, right? Okay, so that's important too. Then if they're doing both, then you say, well, really, nobody cares for throughput and response time. It's really the power that we care for, and then where is the power? You haven't done power. Things like that. So you can always question the metrics. And as I said, if they have done the performance, then you bring up the reliability. If you bring up the reliability, then where is the undetected errors and so on and so forth. There is a whole set of metrics that they missed. And same thing for you. You have to be as careful as possible in selecting the metrics, now that you know how to select the metrics. But at the same time, you have to be prepared to defend your decision as to why you didn't consider undetected errors, why you didn't consider that, so on and so forth. right? And possibly justify that in the paper. Otherwise, your paper will be shut down. So that is the second one. Third is the configuration. Configuration is basically, so what is the configuration? We used one system with 2 disks. Well, 2 disks is just too few nowadays. Most systems have 5 disks, 7 disks. Or if they use 5 or 7 disks, who cares for 7 disks? Most laptops have 1 disk. And so you can always argue as to what is most common configuration. And again, if you are making a presentation, you have to really do some thinking about as to what configuration you are using and why you are using it, and then justify that in your paper. If the other guy doesn't justify, then obviously you raise the question. So that is the third one. Only after these 3 common things are done in any performance study, and which is what most of the papers are actually, regardless of what they are written for, artificial intelligence, databases, operating systems, sensor networks, they're all on performance analysis. So the question is, first 3 things can block you or get you there, but after that only you worry about what the problem is, details. So that is only after that you worry, okay, this problem is about sensor networks, so what is the weakness in your analysis? Before you even get to sensor networks, you can always question the first 3. Okay? So these are rat holes. And then I made a list. I was sitting down in all these meetings with the management, and I made a list of why the management is not accepting the results. This is basically why we are rejecting your paper. Or in the industry environment, this is why we don't like this result, and we won't implement it, or we will not take action on it, or we don't believe what you're saying. So they will not say that we don't believe what you're saying, or that you're dumb or something like that. They will say, oh, this needs more analysis. You just presented them your 1 year of analysis, and they're saying that we need more analysis, which means they don't believe your analysis, period. That's another way of saying it. You need a better understanding of the workload. Obviously, then they will come to the first rat hole, which is the workload. Then they will say it improves performance only for, and this is related to workload, this improves performance only for long IOs, long packets, long jobs, long files, and most of the IOs or packets or jobs or files are short. And this is true. If you measure the IOs on the real system, or if you measure the packets on the real system, or if you measure jobs on the real system, most of them are short. All right? I'm coming to you. And so you can always, if somebody uses the long one, you can say, well, sorry, you missed most of them, because most of them are short. All right? If you, for example, think about what you have done whole day yesterday, and you make a frequency, you will find most of the things you have done is small jobs, small things. Okay? You haven't written 2 papers yesterday, right? Obviously not. You cannot write 2 papers in a day. So you haven't done a big job, you have done a small job. I'm going to come to you in a minute. But if you do small, so if you improve performance only for short jobs, packets, and who cares for the short jobs? It's the long ones, long IOs, long packets, long jobs, long files that impact the system. And that is also true. Is that while most of the things in the world are small, they don't consume resources. Most of the resources are consumed by the big things. So 20% of the big things consume 80% of the resources. So if you think from the resource point of view, then you can say, well, you really didn't model the resources, because resources are not being consumed by these little things. These are the big things that take the resources. And so they will get you there, and they will get you there. And so if you select one of these 2, you have to have a justification as to why you selected that, because now you know this is a general fact of the life. There is a Gibbs law which says that 80-20 rule, actually it is called also 80-20 rule, that 80% of the resources are consumed by 20% of the things. So 80% of things don't, so things which are 80% in frequency do not consume resources, because they take only 20% of the resources. Right? Things that 20% in frequency take 80% of the resources. So that 80-20 rules, you say, well, I know this thing, and so we have actually done a mixture of small and short, or I have done only small because we are really concerned about the response time to all these small jobs, if people cannot wait because, this and that. And, you can say, well, I took big ones because they are the ones that consume most of the resources, and it is the money that we have to put on the equipment that is most important. So depending upon what your reasoning is for selecting one of the two or a mixture of the two, you have to be ready. But this is in general fact of life, that most of the things are small, but the resources are consumed large one. Okay, question.
But isn't the workload supposed to take care of such thing? I mean, the workload.
This is the workload.
Yeah, but I mean, why? I mean, if I decided my workload needs to examine short packets, for example, then I need to know this in advance that my system is working with short packets and not with long packets. I mean, it's not
Right. So here's the thing. Let me just tell you, there's no clear answer to that question as to what is the workload that my system has. One thing you would do is that you could go and measure the graphs of actual systems and then say, well, I just measured it yesterday, and so this is current and everything is okay. So, and that's the mixture generally. It won't be small or large. It would be a mixture, and then you would be in a better shape. All right. On the other hand, if you didn't get to that issue, right? I mean, you didn't have a very representative workload, then you'll have to select. I mean, I have seen papers, people written by, very good universities and everything else, where they said, well, because really most of the jobs are short. I'm just remembering a paper I read 3 months ago. And so we really need to find a way to improve the performance for short jobs. And then he went down and wrote the whole paper, which was for a very significant conference for small jobs only, right? Now, while this person has a very logical reasoning and everything why he worked on the small jobs, but then, somebody could come and argue that, well, this is not really important because they don't consume resources. So that's the point I'm bringing up, is that there are two extremes here, small and short. And one extreme is important. Now, again, you will notice there are two different extremes. One is the user and one is the system. User is the guy, people who are using the system, they care for the response time. And the system is the guy who owns the system. He or she cares only for the total resources being used. He doesn't like that the system is using only 10%. 90% is wasted. So he cares for throughput. The money is paid for the throughput, not for the response time. See what I mean? So the more transactions you make, the more money they will get. On the other hand, if each transaction is slow, the user loses, the system doesn't lose anything. You see what I mean? So there are two sets of people who are interested in this, the user and the system, and response time and the throughput, small and large. So small is of interest to whom? Who cares for the small jobs performance? Who? Think about it and tell me. Anybody? Who would care for the performance of the small jobs? Between the user and system, there are only two answers, user and the system, right? Who will care for the large jobs? Who will care for the small jobs?
I would say both.
No. See, the thing is, one is interested in resources and one is interested in response time. Huh? Yeah, the system is interested in the large ones, whereas the user is interested in short one, because if I go 15 times to a machine and then it takes me 5 minutes each time, I would be very bothered. Right? So I am more interested in optimizing my most frequent work, where the system is interested in optimizing the resources. All right? It needs too much memory, CPU, bandwidth, and the CPU, memory, and bandwidth isn't free. So you wrote this nice algorithm that optimizes the performance of search or database or whatever it is. So it optimizes CPU or memory or something like that. No, it needs too much. Sorry, it doesn't optimize. It consumes. It needs some CPU. It needs some CPU, right? But that isn't free. All right. So next time you take to an algorithm where it saves CPU, memory, and bandwidth, but it's cheap. Memory, CPU, and bandwidth is cheap. Nowadays you can buy several gigabyte of memory, and you can buy so much gigabits and gigahertz CPUs and 100 gigabits network. Who cares for these bits and pieces like that? So both sides they will get you, and both statements are true, by the way. They're true because network isn't free. You cannot get 100 gigabit or 1 gigabit or even 1 kilobit for free, but it is very cheap. You can get 100 gigabit for $20 or $50. So everything is not free but cheap, right? So they can get you from either end, but you can say, okay, well, all right, hold on. I know it isn't free, but at the same time, right now the costs are so low that it is really not meaningful to worry about, having, for example, we were discussing in our old days, how many buffers should a router have? And if you have too many buffers, then the memory would be expensive, right? But nowadays you could say, well, even if I make it 2 gigabyte, it is only $20 or $2 or something like that. So it has to be talked in those terms. You have to justify as to why you care for the memory or CPU. And I have a list of whole 50 such things in the book. You can go through that in your own time. Any questions about these? Okay.
Sorry, is there a right answer to the question?
Yes. Every time, this is where I bring up the art part of it. The right answer to every question is that you have to think about it and justify your answer. Look, I gave you the handout today, homework answer. Thing is, if you justify your answer, that's the right answer. Everybody has a different answer. And so if you don't think about it, you will be caught unprepared. And that would be wrong answer. So you say, well, I want to use simulation, and you don't know why you want to use simulation. Right? Then that is a wrong answer. If you know why you want to use simulation, that's the right answer. It's like, is there a right color for a painting? Okay, so that's the issue, is that both, there are two sides, but you have to think about what is the side that you think is important for the system. So the thing is, again, any of these things, it's not the question of cost of the CPU or bandwidth, it's how much money is going to save after all. So I put a $2 memory into the router, it will improve the performance by a factor of 5, and then the benefit to the customer would be $10 million justified. So you have to go like that. Basically you have to make a case for what you are thinking and why you are thinking that way. So for example, if you really think that it is important to have small jobs, because most people care for the small jobs, you could just then tell the management or tell the people or write the paper that, look, each person spends 5 minutes a day on doing this, and they do it 15 times a day. So that is so many hours a week in a year, and then it's so much costly. So it's better that we improve the performance for them. On the other hand, if you want to do long ones, then you justify on the basis of resources. And so there is no perfect answer. All right, that brings us to the summary. 4 key points. First, we learned about 4 different types of variables: quantitative and qualitative, ordered and unordered, and discrete and continuous. And depending upon them, we either use a bar chart or a line chart. And then we learned that for making charts, there are 3 principles. First is that they require minimum effort from the reader. Second, we require maximum information. And third, we require minimum ink. Those are 3 key principles, right? Then other things are that use not too many graphs, select the ranges properly, so you remember the 3/4 high rule. And then we learned about the common problems, common mistakes in performance analysis, or common issues that might come up in your performance presentations or writing. And those have to do with the workload, metrics, configuration, and details. And they should be carefully selected. You should have justification for them in your write-up. Okay? Any questions so far? None? Then we have a homework. And the homework is very simple. All you have to do is list the problems with the following charts. So write down A and what are the problems, B, what are the problems, C, what are the problems, D, what are the problems. Okay.